स्टार्ट केलंय.
So, okay, simple. Isomorphism of a vector space. So, definition first of all, homomorphism. Homomorphism means linear mapping. Okay, linear means homomorphism. Okay, so now isomorphism extra. So, a mapping, T mapping from vector space U to V is said to be isomorphism if 2 point as in a proof we know isomorphism. So this T must be homomorphism is homomorphism. Homomorphism means linear. Linear and linear means what? T of alpha u plus beta v equals to alpha outside T of u plus beta outside T of v. Combined condition. Linear means 2 point. Okay. T of u plus v and T of alpha u. Combination of this by corollary. So T of alpha u plus beta v is alpha outside T of u, beta outside T of v means linear. So linear means homomorphism. Extra condition for isomorphism 1-1. So this T mapping is 1-1 mapping. T mapping 1-1. Then it is called as a isomorphism. Then we define is a non-singular mapping. Non-singular mapping. Okay, say a mapping T mapping from U to V is non-singular. Non-singular if this mapping T is 1-1 and onto 1-1 also and onto also. When this mapping is 1-1 and onto, then it should be non-singular. Okay. Then what happens? Non-singular, then inverse exists. T inverse from V to U. T from U to V. So T inverse from V to U will be exist. Remember. So for T inverse exist, remember. So this T must be 1-1 and onto, then inverse exist, and then calculate the inverse mapping. We will take example. Obviously, okay. Theorem. Let T the mapping from U to V be linear and non-singular. Then T inverse mapping, from V to U is also non-singular. Is also non-singular, also linear. Both non-singular and also linear. Non-singular. 1-1, 1-2 and linear. Not necessarily non-singular. So only statement, proof is not asked. So then T is non-singular mapping, then T inverse is also 1 1 on 2. Non-singular means 1 1 on 2. So T is 1 1 on 2, then T inverse also 1 1 on 2 mapping. Also linear mapping. It's like statement. This theorem also, we take proof also. So let W be a subspace of U, then there is a homomorphism mapping. Homomorphism mapping of U onto U by W, quotient space. So this we can prove. So let W be a subspace of U. Okay. We define mapping, homomorphism, isomorphism. Define on the mapping. Define mapping. Suppose T mapping from which U to U by W space defined by T of element of U, small u, element of U by W, U plus capital W, quotient space U by W, G by H group. Quotient space elements are okay. Quotients are U plus W. Now verify this homomorphism. So T of U plus V, first point will be U plus V plus W. U there. Now U plus W is the addition of quotients are, which is U plus W plus V plus W. Addition of quotient. Now U plus W is T of U. Defined. And V plus W is T of V. Okay. So T of U plus V is T of U plus T of V. First point. Second point, alpha U. T of alpha U. Reward alpha U plus W. This is same as alpha outside and U plus W. And U plus W is T of U. Okay, so both the points. So therefore T is a homomorphism mapping. Also onto. So onto. So therefore proof complete. Example. Let T is mapping from V3 to V3, 3-dimensional, be a linear map, linear, defined by in this manner. T of E1 is E3, T of E2 is E1, and T of E3 is E2. Okay, then question is prove that T square is T inverse. T square is T inverse. Okay, so first find T square and find T inverse. So first for T inverse, I want 1 1 and 2. Okay, T square. Okay, so given to you T this one, then we find the T square. So T of this like given, T of E1, E2, E3. Okay. So where these E1, E2, E3 are what? Standard basis of V3, 3-dimensional vector space. So then find the T square and T inverse. Okay. So first we find the T square. Okay. So first of all T of x1, x2, x3. What is that? But T in terms of E1, E2, E3. So convert the standard. So this is same as x1 into E1 plus x2 into E2 plus x3 into E3. This like, because E1, E2 are the standard basis. Okay, that's why. Otherwise not this like. Okay. Now T is a linear. Therefore x1 outside T of E1, x2 outside T of E2, x3 outside T of E3. So T of E1 is E3. E3 means what? 0, 0, 1. E2 means what? 0, 1, 0. And E3 means what? E1, sorry. E1 is T1, E1 is E3, correct? 0, 0, 1. T of E2 is E1. T of E2 is E1. E1 means 1, 0, 0 standard. And T of E3 means E2. E2 is 0, 1, 0. So multiply 0, x2 and 0, 0, 0, x3, x1 here. Okay, so T of x1, x2, x3. Then what is image is x2, x3, x1, x2 here, x3 here, and x1 here, cyclic rotate. Then what is T square? Well, in this way, what will be T square double T, T of. So T square of x1, x2, x3 will be what? T of T, x1, x2, x3. So T of, this is already known to us. Okay, is x2, x3, x1. What is T of? What here? Cyclic rotate. This comes here, x3 comes here, x1 come here, and x2 comes here. So this like. So T square of x1, x2, x3 will be this like. Okay, this is your T square. Now T inverse. So for T inverse, I want to show 1 1 onto 1 1 and onto. When 1 1 onto 1 1 nt equal to 0. So first find the nt null space. Nt x1, x2, x3 element of V3 such that T of these equal to 0. By definition, nt is u belongs to u such that T of u equals to 0. Okay, by definition. Therefore, here u means here V3 space. I take separately T of and we solve outside the bracket. Okay, so T of this. So what's T of this? Just we have is x2, x3 and x1. 0 means what? 0 vector. Any dimension. 3 dimension. 3 dimension 0 vector. So if you compare, then x2 equal to 0, x3 equal to 0, and x1 equal to 0. All three zeros. All three 0 means 0 vector. So NT will be contains 0 vector. Therefore, by theorem, T is 1 1. T is 1 1. Onto, of course, as okay, dimension of domain space, domain and codomain are same. T from V3 to V3, 3 to 3, same domain and codomain. Okay, so this is domain and it is codomain. Right. So same. Therefore, onto also theorem is a 1 1 and onto both. So when 1 1 onto means what? T is non-singular. T is non-singular. And then what happens? Inverse exists. T inverse is exist. Okay, so present. So find that T inverse. So let T inverse of x1, x2, x3 is say y1, y2, y3. Say because your T in terms of x, y, z, x1, x. So T inverse from y suppose. Side change, therefore x1, x2, x3 will be equals to what? T of. Now T of by this what? Shifting y2 here, y3 here, y1 here. Okay, compare. So what is y2 will be x1, y3 will be x2, and y1 will be y3. Okay, so put there. So therefore T inverse of x1, x2, x3 that will be okay y1. One is what? Y3. Sorry, is it x3 over last? So y1 will be x3, y2 will be x1, and y3 will be x2. So this third number. Now check t square already we have, and this now t inverse compare must be equal. So from 2 and 3. So t square equals to t inverse. Verify. Okay.